So thermochemistry, right? Thermo means heat. Hopefully you know what chemistry means by now, but we're going to start with this. Before we can start talking about this chapter at all, we have to talk about energy. Now, you learn about energy from when you're a little kid, kindergarten, first, fifth, whatever. You learn about it every year. You learn about it in biology, chemistry, physics, weather, environmental science. Energy is all over the place. And it has a really unimpressive definition, okay? By definition, energy is the capacity to do work. Ugh, I don't love it, okay? Because it doesn't really encapsulate like how amazing and all-encompassing this word is in science. Now, as far as math goes, it has two units, common units. There's other ones. The one that we're going to use most often is the joule. This is the metric unit, and J, capital J, is for joule. But there's also the calorie, like the same as the calories in your food, but actually the calories in your food are kilocalories, in case you're wondering. Now, 1 calorie equals 4.18 joules. Remember that number because that's going to come up later, that 4.18. So now that's a conversion factor that you'll have in case you need to convert calories to joules. So there's lots of forms of energy, right? There's light energy, there's heat energy, nuclear energy, there's kinetic energy or the energy of motion. In this chapter, we're going to focus mainly on heat and chemical energy, but I don't want to forget about the other ones. So I want to run through a quick example that kind of shows you all of these different types of energy. So take a look here. We've got mechanical, thermal, electromagnetic energy, electrical energy, chemical energy, and nuclear energy. And then there's some examples here of all of those. I want you to think about the light bulb in your house right now. I know some of you are sitting in the dark, but in here we have light bulbs. That light bulb is electromagnetic energy, okay? It's visible light. It's light. It's a type of energy. It's reaching your eyes. That's light. If you think about where that light bulb got its energy, you can think about that it was plugged in somewhere, right? So we call that electrical energy. Power lines carry electrical energy into our homes and it goes into electrical outlets. Okay, so if you follow that energy down, you can say, where did the power lines get their electrical energy? Well, they got it from a power plant. And here in Michigan, our power plants burn coal. Not all of them. We do have a couple nuclear and hydroelectric power plants, but around this area, we have coal power plants. Now, the way that coal power plants work is that they burn coal, which is a type of chemical energy. And when they burn it, they produce thermal energy. And that thermal energy turns a turbine, because sometimes when things get heated up, you can get movement of the particles that can turn a turbine. So that mechanical energy gets converted to the electrical energy, right? So the light bulb comes from electricity, which comes from the burning of coal. When you burn things, it makes things hot and it turns a turbine and it creates electricity. So if I think about, okay, fine. So the coal has that energy, has that chemical energy stored in it. Where did it get its energy from? Coal is old dead plants and animals from millions and millions of years ago. So at some point, that coal was a plant, and that plant lived here on planet Earth, and it got smushed over time and it turned into coal, but it got its energy from the sun. So there you go. The one light bulb in our house here in Michigan uses all sorts of energy that's been transferred over time. Now, if we live somewhere with a hydroelectric power plant, we could skip the nuclear energy and the thermal energy and the chemical energy, and we could just, talk about the mechanical energy. But you get the point, right? Energy is everywhere. There's a lot of different types of energy, and these energies can get transferred into other energies. When you talk about energy and you talk about heat energy, there's always going to be a discussion about temperature, okay? And temperature does not measure the amount of heat. So if I were to ask you, what is the temperature of this Expo marker? It's been just sitting here, so it's probably room temperature, about 25 degrees Celsius. Well, is that how much heat it has? No. Okay, that's the temperature. The temperature is 25 degrees Celsius. How much heat does it have? Well, now I've got to do a math problem to figure that out. All right, because temperature and heat are related, but they are not the same. So the equation that we use is Q equals MC delta T. And it describes the amount of heat required to change the temperature of an object. So there it is, Q equals MC delta T. Q is heat, all right? Q is heat energy. Now, if you're wondering why we didn't use H, it's because it's used for something else in this chapter. And if you're wondering why we didn't use E for energy, because it's used for something else in this chapter. But it is a type of heat energy. If Q has been gained, if energy has been gained, it's a positive number. If energy has been lost, it will be a negative number. M, you probably could have predicted this, is the mass of an object. C is something new. C is specific heat of an object. This is something that you're going to have to look up on a table. This is going to be a given, or the problem is going to be set up that you'll have to find the specific heat of the object. And I'll tell you a little bit about it in a second. And the last one, T is the change in temperature. Delta T, delta means change in, so it's the change in temperature. And to find delta T, it's T final minus T initial. Now, people will often ask, should this be in Celsius or should this be in Kelvin? And guess what? It doesn't matter. And let me show you why it doesn't matter, okay? So if delta T equals change in temperature, all right, and it's T final minus T initial. Let's just think about an example. Let's say, I don't know, you have an ice cube and it's 0 degrees Celsius and it heats up to 20 degrees Celsius, right? The change in temperature is 20 minus 0 or 20 degrees Celsius. Now let's rerun this whole thing in Kelvin. If you have that same ice cube, guess what? It's 273 Kelvin and it's going to change to 293 Kelvin. 293 minus 273 is 20 Kelvin. So because it's a change in, it doesn't matter if you do it in Celsius or Kelvin. And this becomes important in your math problems. So let's talk about that specific heat. All right. Specific heat, first of all, has weird units. The unit for specific heat, whenever there's a constant, and that's probably why specific heat has the letter C, because it's representing a constant, it usually has a lot of like funky units because it's meant to cancel everything else out. So the unit for specific heat is joules per gram times degrees Celsius. And that also could be Kelvin if you wanted it to be. By definition, it is the amount of energy needed to raise the temperature of 1 gram of an object by 1 degree Celsius. Okay? A high specific heat means that the object requires a lot of energy to change the temperature. So I want you to think about a cup of coffee or tea or whatever it is. I don't care what it is. Cup of hot water, cup of boiling water. If you take a metal spoon and you put it in that boiling water, they're going to come to what we call thermal equilibrium, and they're going to have the same temperature. When you remove the metal spoon, you have this really hot water, and then you have this spoon next to it. The spoon cools down really quickly. The water stays hot. Everybody can imagine this scenario. You've been here before. Hot pokers, hot utensils, they cool off really quickly, and they heat up really quickly. And that's because water has a very high specific heat and metals have a very low specific heat. So these blocks, right? This one here that feels cold and melted the ice cube really quickly, this is a metal. And this has a very low specific heat. It does not require a lot of energy to change the temperature of this. So this absorbs heat very quickly. That's why it feels cold. Because when I put my hand on it, it's absorbing the heat of my hand very quickly. Okay, there is no cold in science. Cold is a fictitious thing, all right? We talk about heat. Cold is removing heat. This one that's like plastic, this one doesn't have as high or doesn't have as low of a specific heat. So it doesn't remove the heat as quickly. So here's the table. This table is in your notes. You can also Google this. You can find the specific heat of just about anything. I just want to warn you to pay attention to units. I give you the specific heat on this table in joules. Sometimes you'll find it in calories. They're very easy to convert back and forth because we know that 1 calorie equals 4.18 joules. I told you that number would show up again. That's because a calorie is based on water. It's based on the specific heat of water. So on this table, the other thing I want to point out, it does show you the physical states. So the specific heat of water at a liquid is 4.18. But if water is a solid, otherwise known as ice, its specific heat is 2.06. I've got some other liquids here, and then I've got a lot of metals. And you can see here that the metals are a lot lower than the water. But then you can also look at the metals and say, okay, so copper has a pretty high specific heat compared, to like mercury or gold or something like that. And aluminum is something they use for pans quite often. I suppose a gold pan would probably cook things up really fast, but that would be expensive. So here is the way we're going to do these math problems. They're pretty easy. They're pretty straightforward. They're very plug and chug-ish, right? We've got a bar of iron that's sitting at 21 degrees Celsius and it's heated to 83.5 degrees Celsius. So the question is not what is the temperature change? That's easy. The question is how much heat is added? And you need the mass to know the answer to this. Because if you don't have the mass, you don't know how much heat is added. So I want you to start thinking about that. Things that are more massive are going to hold more heat. Things that are less massive are going to hold less heat. So first thing we need to do is find delta T. Delta T, you can either do it in your head, off to the side, whatever. It's T final minus T initial. And it's important that you use final minus initial because it's going to tell you whether heat was added or heat was removed. So it has a final temperature of 83. It started at 21. So delta T is 62.5. And I told you that could either be Celsius or Kelvin. The mass is 551 grams, which is what I've got there. And then the C value, in this case, I had to look it up. It was a bar of iron. So I go to the table, I find iron, and I look it up. And then it's just a simple Q equals MC delta T problem. And when I multiply those three numbers together, I get 15,500. Sig figs do count, right? So this has 3 sig figs. The sig figs in this do not count because that's a given number. And this has 3 sig figs, which is why my answer has 3 sig figs. Here's another example. It's kind of just the same thing over and over again. However, I will take away different variables. Sometimes I'll say, what is the heat added? Sometimes I'll give you the heat and I'll say, what's the specific heat of this mystery substance? So you'll have to find those. So this says what amount of heat is needed to raise the temperature of 450 grams of ethanol, and this is liquid ethanol, it specifically says that, from 10 degrees to 70 degrees, right? So we've got a delta T of 60 degrees Celsius. The C value, I found it on the chart, is 2.44, and the mass is 450 grams. Plug and chug, Q equals MC delta T. Check your units. Make sure that your mass is in grams. Make sure that you put joules afterwards because of this joules right here, which is why this answer is in joules. And you get 66,000. Sig figs wise, this had the lowest number of sig figs with 2, which is why this answer has 2 sig figs. So that's how you do the math for these. And like I said, depending on the problem, there will be different variables missing.